Well, hello everybody and welcome to MI212, our semester-long webcast on advanced topics in population PK/PD modeling and simulation. This is Mark Gastonguay again, and welcome you back to our first lecture here in this series. And today's topic is going to be focused on some of the advanced pharmacostatistical topics in modeling and simulation. In particular, we're going to be talking about inter-occasion variability and mixture models. Now, you should all have seen that the course handouts are posted to the website. In fact, let's just take a look there for a moment. Back to the course website. And today is week 2, advanced pharmacostatistical topics, IOV and mixture models. So you have the chapter 1 notes there, as well as the assignment for next week. Remember that if you have technical difficulties, don't hesitate to contact Joseph Hebert. The information is provided in the course materials, as well as on the GoToWebinar chat. If you have questions about the material as we're running through here, don't hesitate to post a question using the question interface box as part of the GoToWebinar control panel. So just following up on some of the assignments from last week, we talked about preparing for the rest of the course. One was to log into Simi, check your login accounts, edit a file, save it, download it, just get used to some file manipulation procedures, to log into the course site, listen to the recording, make sure that worked, and then to read a couple of papers. The first two elements, I think, still have not been completed by everybody, and just from our informal poll at the beginning of the class, there's at least 50% of the class who has not done this yet. So please don't hesitate and do that as soon as you can, hopefully today, because Friday we'll be working live in the lab session with the Simi interface. So please work that out. Let us know if you have any technical difficulties. Usually these are just browser issues, turning on cookies when we need to, or something like that. It's not a major issue, but you don't want it to get in the way of your participation in the hands-on work. And then lastly, I'd asked you to read a couple of papers, and we'll cover the substance of the modeling components of these papers in the class today. The first was a classic paper that first defined the inter-occasion variability random effect in population PK. And then the second was sort of a summary of results of using mixture models and making that assessment for a particular subpopulation and how that impacted decision making. It's kind of an interesting paper, not so much a technical implementation, but an interesting survey of the literature. Okay, so hopefully you got through those pieces, and we'll get back to the course now. So we'll start with, I'm going to request to increase the volume here, and I've got it at the maximum. So if you're, just one bit of advice, if you're not receiving adequate volume for the audio, please use a headset I think that's the optimal way, is to use a headset, preferably USB, but you could also use the typical radio type headset jack on your computer, and make sure that your internal settings for output volume are maximized. Okay, on to the first topic then. You'll see that the notes here just review some of the stuff that I covered last week. Basic course requirements, the server itself, the course materials, and how you can access those. What we're going to do now is start into the details of these two new topics. Inter-occasion variability, and I'll talk about what that actually means and how we implement it. And then we'll roll into another interesting topic called mixture models. First, understanding why we need mixture models in the parametric type nonlinear mixed effects that we're implementing here in NONMEM. We'll talk about implementation in NONMEM, show you the NMTran code, and then we'll have a practice problem that I'll introduce, but we'll actually execute on Friday's lab session. Inter-occasion variability. Well, this is really can be thought of as another level of the population model random effects hierarchy. NONMEM formally only allows 2 levels of random effects, and if you took the MI212 class, you'll be familiar with this concept of nested random effects, where we have the residual random effects at the observation level, and we have inter-individual random effects between subjects. Well, we know that we can implement those in NONMEM by specifying a variance-covariance structure in $sigma for the residual and $omega for the inter-individual, assuming we're running a population model. But there isn't a third grouping variable. And we'll see as we go to the implementation that we're going to use a bit of a trick here to use the omega level to specify that third level. But essentially what we're trying to do here is specify another level of variability, and that's the variability within subject from one occasion to the next. So if there's no systematic trend over time, you'd expect that variability to have an average or an expected value of 0. But there can be deflections in the positive and negative direction for various PK parameters from occasion to occasion. That's what we're going to work on here. Inter-occasion variability can be a useful diagnostic of systematic variation over time, but it's really not an appropriate mechanism to model that type of relationship. So for example, consider a system where you have a time-dependent pharmacokinetic process, maybe an autoinduction of metabolism. And in that sort of a scenario, you're going to have an increasing clearance over time. Well, you could model that on multiple occasions, and what we're talking about here for occasions are usually different visits where there's some intervention or sampling going on. So you might have a longitudinal trial with follow-up visits every 2 weeks for 3 months. Well, those follow-up visits every 2 weeks are going to be visits where the some observation made, it might be pharmacokinetic, it might be a pharmacodynamic or outcome observation. But the model will be allowed to change in its parameters or a subset of parameters from that one occasion to the next. If we go back to that idea of a time-dependent pharmacokinetic system, the autoinduction model, you'd have an increasing clearance over time, but that would be a systematic change in that, at least up until some potential maximum, the clearance would be steadily increasing from one visit to the next. That's a systematic variation. It's not what we're talking about for inter-occasion variability, which is assumed to be a random effect. It's not systematic. Inter-occasion variability might be more easily associated with something like random variability in drug adherence patterns, or maybe adherence to labeling instructions with respect to taking an oral medication with food. You can imagine that over time there might be some fluctuations in the relative bioavailability, and that may be an inter-occasion variability on the relative bioparameter. Might be a reasonable thing to do to account for those occasion-specific differences in the input. Maybe taken with food on one occasion, without food on another. Maybe the entire dose wasn't taken for that week. And so that's one way that we can model this sort of random variability. But the point is that we would assume that pattern of variability would be random and not systematic. Now, if that pattern of variability was dependent upon something like a disease progression that made it difficult for the patient to swallow the oral tablet, maybe something like myasthenia gravis or Parkinson's disease, then you might see progressively systematically changing bioavailability because of poor compliance, for example. That would be a systematic change. So really what I want to contrast here is systematic variability across occasions versus random variability. IOV is focused on random variability. Now that doesn't mean we can't use IOV as a diagnostic for systematic changes. And in fact, if we did model inter-occasion variability over time and looked at the trend of those inter-occasion random effects, it could be possible to identify maybe something that's systematic underlying in that system. And then that would require further investigation to see what components of the fixed effect model need to incorporate that systematic change. So the reason that we do this is really twofold. One is that it's shown to improve the population parameter estimation precision and accuracy. If we get the IOV correct, or at least if we account for it, we'll improve the precision of the fixed effects parameter estimates and the variance terms as well. And furthermore, it also is helpful when we turn around and we use this model for simulation, in that if we've captured inter-occasion variability accurately, we might be in a better condition at predicting a new data set where, in a new study where there are multiple occasions, by partitioning out that IOV from the residual random effects and the inter-individual random effects. Okay. Implementation of this is not so straightforward, but not so difficult. Like I mentioned before, NONMEM only allows for 2 levels of random effects in the hierarchy, but we can use that L1 level, the omega for inter-individual random effects, to represent 2 different distinct levels, inter-occasion and inter-individual. So what we would do is implement a random effect that is specific to each occasion, in addition to that eta random effect for the inter-individual difference, and where each occasion is specified by some indicator in the data set for visit or occasion that carries a unique flag that's only present with a value of 1 on a specific occasion for each data record. So in other words, that random effect is only coming into play on a given occasion. And then another trick that we use here is that we do this across multiple random effects, but we constrain all of those random effects to have a common covariance matrix. And we use the same option under $omega to do that. So let's take a deeper look. Here's the data set, or a template of a data set. And we have the usual suspects here, a comment column, which is user defined, but the ID, dependent variable, amount, interdose interval, the additional data item here, if it's a multiple dosing setting. Time, of course, obviously now we have a 0 order input in this data set, which is a rate of 300 per whatever the time units are. And then we have a visit indicator. So let's pay attention to the visit and event ID here. We have the first record is a dosing record. It's a dose of 900 every 12 hours for a total of 10. This first one plus 9 more. And that's some 0 order input. It might be a constant rate infusion, or it might be some known oral release formulation or something, but it's at a constant rate. And we see that's administered And there's a particular visit here, visit 1, where PK samples are taken over time, up to 144 hours. And then later on, there's another visit, visit 2, and we don't really know how far in time that this visit occurs relative to the first because we don't have a cumulative time indicator. You see, each one of these time starts at 0 for each occasion. The reason we can do that is because we're resetting the system at each of the dosing events. The first dose is set at an event ID 1. And if you recall from the last class, the 210 class, event ID 1 is a dosing record. Event ID 0 is an observation record. And event ID 4 is a combination of a dose and a reset. Actually, first a reset, then a dose. And so what this system does then, it calculates, according to this dose and dosing regimen, what the predictions would be at each one of these time points for visit 1. And then before going to visit 2, establishes a reset. So in this example, it's assumed that there is no accumulation, no carryover of pharmacokinetics from this first treatment. And in fact, it might be a crossover design with a washout. If it's a crossover with washout, that means that there is no residual drug, or hopefully you've washed out long enough that there isn't. So you reset the system, give the dose with this event ID 4, and now you run your sampling series on visit 2. And then the same thing's done for visit 3. So this might be a 3-way crossover design. All of these records are happening within individual 1, and this is the only time in an NMTran data set where you can have time that is not chronologically sorted across the whole individual, and that's because of the reset. If you didn't have this reset, the NMTran would choke on this and would tell you that time is not sorted correctly because all of a sudden you're going from 144 to 0. Okay, so this is one strategy for a design that might be sort of a crossover with washout. It's exactly the type of example that was used to first identify the importance of IOV by Mats Carlson, Lou Scheiner, and others, in that there were biased estimates of the relative of the PK parameters across those occasions when looking at this crossover in terms of a bioavailability, bioequivalence type study. It looks like I've got a question on the data set here. What is the first column C for? That first column, sorry about that. If you followed with the course last semester, we often use the C column. This is user defined. I've made up this variable. I use it as a comment indicator, and it's an easy way for us to comment out a data record because we can then include in the control stream the ignore equals C option. Any row that begins with a C here could be commented out. The other nice thing about having a separate column to do this is because you can comment out a row without actually altering data in that record. Okay, so it's just the comment column that gets altered. We don't have to add a C in front of the ID here. So that's all that's for. So while we're talking about data structure, another question here is related to a much more complicated question. What happens if you have multiple studies? And I'm assuming that they have differing visits, yeah. So to read the question further, with differing visits, one has 2 visits, the other one has 3. How are they coded? So that's really something that the analyst has to make a decision about. And what I would usually do is to view the same sort of time period in terms of visit. I think that's the most useful thing to do. So if you have a longitudinal study with biweekly follow-ups, and you have one that only runs for 1 month, and then another one that runs for 6 months, but you have the same follow-up pattern, I think it would be fine to include those all as separate occasions. And at least we know that random variability is occurring over the same basic sort of sampling interval. It gets a little more complicated if you have different intervals, long-term changes. But I think it still is beneficial, even if the duration is different and the number of visits is different, to still include that inter-individual random effect, because really all it's doing is allowing you flexibility for the PK parameters to be different within subject from one occasion to the next. But ideally, if you had the ability to group this or to design it yourself, a similar interval would be helpful. It doesn't matter that one trial might only have 2 visits and another one might have 5 visits. There still is random variability within subject between those occasions, and you would just code it as such, where the first trial might just have visit 1 and 2, and the other trial might have visits 1 through 5. Okay, so that's the data set. Let's look at the code. And I'm giving you just an excerpt here from a control stream. We're modeling inter-occasion variability in clearance and volume for this example. It's a constant rate IV input, so this is actually clearance. It's not relative to bioavailability. And the way we're doing that is by accommodating those different occasions. So we've got an occasion variable in the data set, or visit variable. Occasion 1 is equal to 1 on visit 1, and it's 0 otherwise. Occasion 2 is equal to 1 on visit 2, and it's 0 otherwise. And occasion 3 is equal to 1 on visit 3, and 0 otherwise. So the important thing here is that each of these occasion indicators takes on the value of 1 at a specific occasion, and it's 0 at all others. And then we don't have duplication of that occasion random effect value equal to 1 on the same occasion. That would cause an identifiability problem. Okay, so let's see what the code looks like. Clearance is equal to some typical value of clearance, which is defined elsewhere, times some exponential random effects. And so this parentheses here specifies all of the random variability associated with clearance, not just inter-individual, but also inter-occasion. So you can tell which components are which here. We have A to 3 times occasion 1 plus A to 5 times occasion 2 plus A to 7 times occasion 3 plus A to 1. Well, all of these with the occasion flag are the inter-occasion random effects. And this last one here, the A to 1, is the random effect associated with the inter-individual variability. It's not occasion specific. This is just inter-individual variability. And this basically sets your average across all occasions for that individual. These other random effects allow clearance to be different from one occasion to the next. Same thing for volume of distribution. We have A to 4, 6, and 8 that are the occasion specific random effects. And then A to 2 is your inter-individual random effect for volume. Okay. Well, that's how we write the model. Now the trick comes in how we constrain the omega estimates to specify these different variances. So let's keep track here. A to 1 and 2 are the inter-individual variability. And so we can set up for those an inter-individual covariance. We're using a block 2, meaning that we're going to define both the variances and the covariance term. And that's our inter-individual random effects, just like you would always do with a simple block 2 inter-individual covariance matrix. Now we get to the inter-occasion variability. And we're going to have a separate block for each occasion. And inter-occasion variability is also allowed to covary within a subject. So we could have different occasions varying together. Now the next two elements of omega, so the first two, 1 and 2, were part of the inter-individual. The next two are A to 3 and A to 4. Those are inter-occasion random effects on clearance and volume respectively. So we can block those together, assuming that maybe there's a covariance between them, and specify initial estimates for those for the inter-occasion variability. And it's just coincidence that I've used the same numbers for IOV as I have for IV. In fact, the inter-occasion variability might be quite different. Maybe it's much smaller than the inter-individual variability. So you could specify different estimates there. Then your next two terms, eta 5 and 6, again for clearance and volume respectively, those are just inter-occasion again, but for a different occasion. And same thing with 7 and 8. Well, if we keep the theory in mind here, what we're doing is we're specifying an inter-individual covariance matrix, or an inter-occasion variability across all occasions. It's just that we need to use this occasion-specific indicator in order for that random effect to have an impact on separate occasions. But they're really all coming from the same inter-occasion variance, right? So the variability around all of these inter-occasion random effects from clearance comes from one variance distribution. The variability of all the inter-occasion random effects for volume comes from one variance distribution. And there might be a covariance between the two. So the way that we implement that is, although we have defined them as separate blocks, we're essentially saying that the random effects can be different, the individual inter-occasion random effects, but the variance of those terms is the same in all cases. And same here just indicates that the same variance structure and same variance estimates are used as the preceding block. So this says that the second block defines the inter-occasion covariance. The third block just specifies the random effects for another set of occasions, but under the same covariance, and the same thing with the fourth block. That's why the same option is used. And this is the trick that we use to take that inter-individual covariance matrix and turn it into another level of random effects. Okay, so the key concept here is that we allow a random effect to vary from occasion to occasion, but within a given parameter, such as clearance, when we summarize across all of the inter-occasion random effects, those all arise from the same distribution, the same variance distribution. And that would be the inter-occasion variability on clearance. Okay. Any questions on that? Looks like we have one more question. Does this model actually need eta 1 and eta 2? You could write eta 3 star as eta 3 plus eta 1, etc. Yeah, I'm not sure what you're getting at there, Andreas. I think we do need the inter-individual random variability. If you don't have that eta 1 and eta 2, you don't allow the individual to be different from another individual. And so we might have inter-occasion variability within a subject, but all the variability would be centered at the population typical estimate. So we need that individual to be able to shift from the rest of the population, and that's what eta 1 and eta 2 are doing in this model. Okay. All right, well, let's take a look at the NM7 help on this topic, just for a little further detail before we switch gears to mixture models. And there's a couple places we can look here in the help files. One is under examples. There's an inter-occasion variability example. And this is actually one that comes from an early work, again by Carlson and Shiner, describing IOV in a parameters subjects between study occasions. You'll notice a similar structure to what I just described here, with the event ID having values of 0 and 1, and they use a number 3 reset event. Remember, the number 3 reset is a reset without dosing. Number 4 is a reset and a dose. So a number 4 is sort of like a number 3 followed by a number 1 on event ID. Okay, so you'll see, let's look at the data first. You'll see a similar structure here. Well, we don't have the columns. Pull up input. ID, age, race, height, hydrochlorothiazide use, amount, time, dependent variable, event ID, steady state, II, and occasion. So those last variables, the occasion, this is a simple two occasion occurrence, same ID, very similar structure to what we talked about here. And you'll see one difference from what this NONMEM manual shows us from what I showed you is this column here, this fourth to last column, that's event ID. Yeah, and so you start off with an event ID of 1, have all these, which is the dose, first dose, have all these observations, and then have a reset, and then start with event ID 1 and all these doses. Well, remember what we did is combine these two rows into one, where you don't need this row with the reset. Just use event ID 4 on this next dosing record, and that does the same thing. Essentially, it's very similar to what we're doing in the example I've already presented to you. This one has inter-occasion variability on clearance volume and Ka. Let me expand this font a little bit. So very similar structure. Eta1 and Eta2 are the inter-individual random effects for clearance and volume, and Eta7 is the inter-individual random effect on Ka. You have 3 and 5, which are inter-occasion random effects for clearance, and 4 and 6 for volume. Etas 8 and 9 are inter-occasion random effects on Ka. Now this one is a little more complicated in the structure because we have two different blocks here. So if we go Eta 1 and 2, and again, remember you have to just follow the numerical order here. So 1 and 2 are inter-individual random effects. Here's omega block 2. That's the inter-individual variability on clearance and volume. Then 3 and 4, those are inter-occasion random effects on clearance and volume, and so are 5 and 6. So this next block specifies the inter-occasion variability on clearance and volume, and then we have omega block 2 same for the next two occasions. But the thing that's different is now we also can specify an unrelated block. For example, Ka here is modeled independently. There's no covariance between the random effect on Ka and clearance and volume, and so that's specified down here with a variance term 1.2. There's an inter-occasion variability, which is assumed to be 0.5, and it's just a block 1 because it's just a single variance term. And then the other inter-occasion random variability is also set to be the same. So this is how you'd structure it if you had a combination of block and diagonal inter-individual random effects. And there's, yeah, I think that's all that we're going to look at here for inter-occasion variability. It looks like a few more questions, so let me pull up the dialog box. To generalize, can we model as many hierarchical levels as we want in NONMEM? Say different sites, different studies, etc. No, that's not a generalization you can make in NONMEM. The problem here is that the reason we can use the omega is that it is still keyed in on the same ID. And now we're looking at occasion within ID. So if you had some random effect that was sort of structured like that within ID, you could model it in this way. But this does not allow us to model as many hierarchical levels as we'd like. Different studies, different sites, and so on. That's just, it's not possible with the current implementation of the NMTran model specification language. Hope that answers that question. Go over the same again. Yeah, I'll explain that one more time. It's a little bit tricky. Took me a couple times to digest that. Let me go back to the notes. Think about it this way. If we have inter-individual random effects, those are defined by this initial covariance matrix. And that's completely independent from IOV. But now we have inter-occasion random effects. And inter-occasion random effects are structured such that we need a separate eta for each one of those occasions. Remember, the eta is going to be some value that comes from a distribution, mean 0, and a variance of omega squared. It's going to be centered at 0, but it can be some positive or negative value. So maybe the first occasion this individual's clearance is higher than it might be on average. And then the next occasion, maybe it's lower. So that's a positive eta 3. It's a negative eta 5. And then maybe it flips back to the positive side again on eta 7. So this individual's clearance is bouncing up and down over occasions. Eta 3 is positive, eta 5 is negative, eta 7 is positive. It allows us to account for that variability, but the assumption that we're making is that eta 3, 5, and 7 are really all random effects coming from the same distribution, this inter-occasion variability. Okay, it's not that we have an entire distribution of eta 3s, an entire distribution of eta 5s. No, we only have one eta 3 for this individual. And so what we're really looking at is the inter-occasion variability within this subject, and assuming that it derives from a variance that is the same. All of these random effects are sampled from the same variance. That's why we use the same block here. So we just specify the inter-occasion variability covariance once, and then every other pairing or every other random inter-occasion random effect is just specified as the same structure and same parameter estimates for the covariance. Okay. Is it always same? And in what scenario should we implement a different variance? No, it's always same. We have to make that assumption because it's not identifiable otherwise. If we're trying to estimate the variance of these random effects that are occurring over an occasion, they've got to arise from the same distribution. Okay. When we code IOV, do we assess it on all parameters at once, one at a time, or is it based on some prior information? That's a good question. And you could look at this as sort of a stepwise regression approach where you just try it on everything. I think that's overkill, and in fact, you got to realize that anytime you add more variance, that the objective function is going to drop. The variance term is in the denominator of that objective function, and anytime we add more variance to a system, it's going to improve goodness of fit. It gives you more flexibility. So what I would do is potentially base it on some hypothesis for a mechanism, so that whole idea that an individual's relative bioavailability might be changing for an oral medication over time because of differences in administration, maybe compliance, maybe adherence to instructions to take with food or without food. That's a pretty practical way. If we know that an individual is critically ill and their potentially their organ function is fluctuating depending upon their disease status, but we don't have a measure of that disease status, well, we might say that clearance might be affected here, so let's look at IOV on clearance. Ultimately, you want to assess this by performing some sort of a simulation-based model check, and what I would typically do is do a predictive check to make sure that you're capturing the variability between occasions as well as the variability between individuals. And so pick some sort of a metric that addresses that. For example, you might take the observed variability in a measurement within a subject across multiple visits. Okay. What parameters are described in the covariance matrix? Okay, so just to be clear, the covariance matrix here is the covariance of the random effects on clearance, and this is part of the basic course that we teach. But what we're talking about here is an omega block is the covariance matrix structure for the inter-individual random effects, and it's ordered according to the numbering of the etas. So eta 1, which is associated with clearance, is the first element here. Eta 2, which is the random effect for volume between subjects. is the second element, and this middle element is the covariance term. So this is a lower half matrix. If this isn't clear to folks, it's probably worth a little bit of catch-up work on some of the basics outside of class. Okay, so in this example, occasion 3 is set to primary etas. Now let's look at this. Just look at the coding here. So we have occasion 3 is associated with eta 7. Occasion 2 is associated with eta 5. Occasion 1 is associated with eta 3. And eta 1 is the interindividual random effect. So if in the terminology of this question, when you say primary etas, I think you're talking about interindividual random effects. Well, that's eta 1. Okay. All these other random effects are occasion-specific random effects. Okay. Now the next question here. By the way, I'm pleased with all of the interaction here. If any of this is not clear, don't hesitate to type in some more questions. There's one more here. I wonder how we model the variability above level ID, such as interstudy variability. Interstudy variability is difficult, and off the top of my head, it's not possible when you have all these other levels. Now you could do it if you were modeling summary level data where we had inter-study variability, maybe inter-arm variability, and residual variability. But when we are modeling residual, inter-individual, inter-occasion, it's not possible to add another level such as interstudy. Okay. I think we've gotten through all the questions now on IOV. Okay, one more question. I'm a little confused about the relationship between visit in the data file and occasions, especially as these are commented out. Okay. So occasion here is a derived variable. I haven't shown you the code for how this is calculated, but let me look at the help file here from NONMEM 7, and it will show you. I'm assuming here that you can make that translation from a visit of 1, 2, 3 to an occasion of OCC 1, OCC 2, OCC 3. And the way you would do that is you'd write code. In fact, I'll just type in a little piece of code here. Let me make this a little bit larger. So if visit, or it might be called viz in the data set, equals 1, then we might say OCC 1, occasion 1, equals 1. And I might preface this by doing something like this. OCC 1 equals 0. Oh, sorry. OCC 1 equals 0. OCC 2 equals 0. OCC 3 equals 0. So we initialize them all at 0. And we just specify if-then statements, or actually just if statements for each of the elements. If viz equals 2, then occasion 2 is equal to 1. Okay, if viz equals 3, occasion 3 equals 1. So now what we've done is created a binary variable out of this 3 categorical variable. And we have 3 binary variables, actually. They're 0, 1 variables, and they're only taking on a value of 1 at their specific visit. If you had more visits, you would just need to define more of these binary variables. Okay, so if you look at that next to this equation, you'll see that occasion, so let's say it's visit 1, OCC is 1, OCC1 is 1, OCC2 is 0, and OCC3 is 0. So OCC1 would be turned on, A to 3 would be part of this prediction on the first visit, A to 5 and A to 7 would not. Okay, that's defined in the NONMEM 7 example. Another question is for interstudy variability. Could you consider study as a covariate? And you could include study as a covariate. That's sometimes difficult to explain on the back end, but if you think there's a specific difference based on study, it would probably lead to more precise parameter estimates and less biased estimates if you accounted for study as a fixed effect. Okay, let's see. For identifying fixed effects that might replace the random effects in a model, one can graph the random effects against the covariate values. Is there an equivalent for IOV? Yeah, so you've got to be careful with that. So when we look at inter-individual variability, you plot versus a covariate, and assuming that individual has that covariate is constant within the individual, you can map out that relationship. So in other words, you have a covariate value for each individual, and you have a random effect for each individual. Well, now it's a little more complicated because you have more than one random effect over the course of time for an individual. So one useful plot for looking at systematic trends would be to look at the random effect, the inter-occasion random effect trend as a population now versus time. And that might indicate if there's a consistent systematic shift in clearance over time in the population. You could do that with like a spaghetti plot that connects each occasion random effect value over time. You could also then plot that versus any time-dependent covariates. If you have predictors that are not dependent upon time or not changing from occasion to occasion, then there's no reason to suspect that they're explaining the variability from occasion to occasion. It has to be something that's tied to the visit or the time. But we've used this approach many times to sort of diagnose time-dependent pharmacokinetics due to some other cause by just plotting these random effects versus time. Okay, so another question here, another suggestion is, couldn't we model interoccasion variability by defining one theta at visit 1 and a different theta at visit 2? Is this also correct? Well, what you're saying in that case then is that the population typical value is changing from occasion to occasion in the same way. That's completely different than what we're doing here with IOV. With IOV, we're specifying a random variable term that may be deflecting in different ways for different individuals. So if we use a theta to code interoccasion variability, what we're saying is that the entire population shifts in the same way. And that's where you're getting at, again, the systematic change in a PK parameter. That's not a random interoccasion variability. The reason we use a random effect is so that some individuals can have maybe a higher clearance on occasion 1, a lower clearance on occasion 2, whereas others might be low on occasion 1 and high on occasion 2. It allows that flexibility, and it's really not systematic, so it cannot be implemented using a theta. Again, when I say theta here, just to get the jargon out of the way, the theta is the population typical value for that parameter. Okay, those are all really excellent questions. I hope that that this makes a bit more sense. We're going to explore this in the example on Friday. And again, if you're still unclear on some of this, you can listen to the lecture notes again or listen to the recording, but go back and read some of those papers that I pointed out, particularly the Carlson-Shiner paper. All right, now it's time to switch gears to the next topic. which is mixture models. So before we can understand why we might need a mixture model, we got to talk a little bit about the assumptions in parametric versus non-parametric estimation methods for population nonlinear mixed effects. And we talked about this in the first class, but I'm just going to review it again now. Remember, parametric methods have an assumed distribution for the random effects. For example, in NONMEM and in most of the parametric methods, we assume that the inter-individual random effects arise from a normal distribution, mean zero and some variance. We call it omega squared. There's a structure for that random effect distribution. We do check that our assumptions about that structure are correct, but we are making that assumption every time that we run a parametric nonlinear mixed effects method. And that basically applies to all of the methods in NONMEM, except the non-parametric method, NLME and S+, and most of these other nonlinear mixed effects tools. Now there's another way of approaching this. The reason that we make that parametric assumption is so that we have some structure around the partitioning of the noise or the variability. Remember, we have two levels, so we assume that there's a residual random effect at the observation level that follows a normal distribution, and that's at every data point. And then across individuals, we have this inter-individual random effect which follows a structure. In order to estimate both of those, we've got to have some structural constraint on them. Well, there's another school of thought called the non-parametric method, which doesn't make that assumption about the inter-individual random effects. So there is no constraint on the distribution of the inter-individual random effects, but in order to do so, you've got to constrain something else. So what's usually done is that the residual variance model is known and fixed. So in this case, what's often done is the assay error is calibrated, and that assay error is fixed according to some polynomial function, potentially, is fixed in your estimation model, so that the residual noise is known. Sometimes there's a proportionality constant multiplied by that polynomial, but essentially what you're saying is we know the residual variance up to a proportionality constant. And therefore, anything else in that variability is inter-individual variability, and we'll just estimate it discretely. And that's what these tools like NPEM and PML and NLMix and a variety of these types of tools use. And that's fine, but you're also making another assumption. You're assuming that everything that's not part of that assay variability is inter-individual variability. And there are, as we know, there are many other sources of variability. There's inter-occasion variability, but there's also things like process noise, the conduct of the study, errors in recording dosing times and sampling times. All of these things factor into the model misspecification itself. And so if we restrict the magnitude of that residual variability to be just the assay noise, it could be that we maybe partition some of the remaining noise into the inter-individual bin, maybe inappropriately. I'm not going to pick one side over the other, but I just want it to be clear that there are assumptions being made with both methods, both parametric and non-parametric. And you might hear criticism of one method or another from various camps or advocates, but the basic truth is that both methods make assumptions, and what we need to do is to check the assumptions and how they might impact our analysis and the decisions we make from that analysis. So having said all that, what we're talking about with mixture models here is a way to solve a problem in a parametric model where the assumption is not met originally. So let's take a look at this. In this plot, we see inter-individual random effects on clearance for a population of individuals. Our assumption about this is that the inter-individual variability is normal and centered at 0. What we have actually in this case here, this is a skewed. This may be actually the clearance itself because it's not centered at 0. But what we clearly see is that this is not normal. We've got this sort of bimodal distribution here. We get a peak down at this end and then a larger density over here. Well, this sort of distribution does not match our assumptions about parametric random effects. And essentially we're in violation of those assumptions and the method may not be valid. If we were to walk away and leave the model as is, all of those criticisms that come from maybe the non-parametric side would be valid. But what you need to do then is think about how can we fix this? So there are different ways to try to fix this. You could try to change the structural model. Maybe that's the problem. Or maybe there's a covariance term that's not being accounted for. Maybe you have a difficulty in identifying the parameters at the individual level, and you might need to simplify the omega matrix or constrain the model to avoid flip-flop, for example, in a PK system. All these things are possibilities. But if you exhaust all of those, it might be that we have a parametric distribution of etas, which means that we've got maybe 2 populations of individuals here with maybe different means and potentially different variances. Okay, so what this plot might represent is maybe it's a covariate, a categorical covariate that we haven't observed, maybe genotype. In fact, this is a very useful way to deal with polymorphic metabolic systems if you don't have the genotype covariate. But maybe we don't have that genotype covariate and we have this distribution and clearance in these 2 modes. Well, we can use a mixture model then to estimate the probability of each individual belonging to one or the other population, the fraction of individuals in one or the other, and the actual point estimate, the mean and variance of the PK parameter for those 2 populations. This is really part of the assumption checking, the distribution of etas. And in the model without the mixture, one of the places we can look is by making those types of histograms. The eta bar diagnostic is also one that can be useful in identifying the deviations from our assumption about eta distributions. So we can try to modify the model, but there may be some underlying unknown reason for that, for example, an unmeasured covariate, and that's what I'm talking about here. Now here's an output from NONMEM. It's an eta bar output, and you see, in this case, if we had accounted for the variability correctly, the first row here represents the individual eta bars, which are the means of the individual etas, and the p-value for the test that they're significantly different from 0. In this case, none of these are significantly different, so we're okay. However, if you had one of these that was quite small, less than 0.05, and your histogram showed that sort of bimodal appearance or appeared to have a non-normal distribution, that's when you would consider modeling a mixture distribution. By the way, while we're talking about eta bar, there was a bug in NONMEM 6 that the eta bar calculation was not correct when using a mixture model. In NONMEM 7 that's supposed to be fixed, but I have not confirmed that myself. So that's something to pay attention to. And again, more of the same model checking. This is a case where it looks like at a base model there is some skewness, maybe 2 populations clustered close to each other here on the left side, whereas it's resolved on the right side. But this is one that was solved without modeling a mixture, was just by including covariates in the model. So the take-home lesson here is to first exhaust the other possibilities. Look at the structure of the model, look at other covariates, look at other possible explanations for that non-normal random effect distribution. And after you've exhausted everything and you still have a non-normal distribution, and particularly if it looks bimodal, that's when you would maybe entertain the possibility of a mixture model. Okay, so I've already described this in some detail, but remember, this allows us to describe unknown mixtures. We model inter-individual variability as two or more subpopulations. And for each of those subpopulations, we can estimate different fixed effects parameters and different variance parameters. So you can have a separate theta and omega for each population. We also will estimate the fraction of individuals in each population, and this is an estimate that we derive as part of this, and we'll assign each individual to its most likely subpopulation so that for each individual we get a mixture population assignment. Poor metabolizer or extensive metabolizer, for example. So you can see this is pretty valuable stuff, and could be quite useful in those cases where you do have this, a categorical predictor, potentially a genotype type covariate that is unknown, but you still want to account for the variability accurately. Okay, so that's why we might model this, and here's how. There's a few more components to the control stream that we need to consider. One is MIXNUM. And this is an internal variable that is set as NONMEM does the mixture model estimation. MIXNUM is set to, well, assuming two populations, 1 or 2, according to whether PK's computing parameter values for the first or second populations, respectively. And essentially what's being done under the hood here is that each individual is being modeled as possibly belonging to one population or the other. And then there's a decision criteria based on goodness of fit that allows the assignment of the individual to one population or the next. The mix est for each individual, then NONMEM computes an estimate of the number of the subpopulation to which that individual belongs. And that's what's stored in mix est. So if you have a two population mixture, individual 1 might land in category 2. Individual 2 might land in category 2. Individual 3 might have a mix est of 1 in category 1. Now, unfortunately, we can't display that variable mix est in the tables and plots and so on. So we can capture it in this thing called est, EST, which is defined in the control stream and can be displayed in tables and scatter plots. So that's going to just tell us the estimate of which population the individual belongs to. Excuse me. So here's the implementation in a control stream. Again, I'm giving you just a segment of this. The dollar input, dollar data, dollar prob are typical. But here's the new stuff. Maybe we saw that plot that I showed you earlier that looked like it had a bimodal distribution. And this one is going to assume that we saw that plot for both clearance and volume. So when we initialize this, we want to define est as the mix est. Mix est, remember, is the internal specification of the subpopulation. Est is a variable that we can capture this in and include in our table. And then we use if-then statements. So MIXNUM is an internal variable in NONMEM specifying the population. So if MIXNUM is equal to 2, so for example, if we're estimating population number 2, then we can specify parameters for this model. It might be easier to look at the else condition first. What we're saying is if MIXNUM is equal to 1 or not equal to 2, we're going to specify clearance as a fixed effect and some inter-individual random effect, and volume is the same. Okay, so that's the condition for the first population. If MIXNUM is 2, we're going to define these parameters, and it's kind of tricky in its implementation here, but look at it carefully. What I'm showing here is that we're using the same theta, theta 1 for clearance and theta 3 for volume, and all we're showing is that the difference is this multiplicative factor. So theta 2 and theta 4 is the fractional difference between populations. You could, if you'd like, instead just use a completely new term here for theta and just compare the point estimates themselves. But this is kind of a nice way to do it because it allows you to say that one population is X% of the other with respect to clearance and X% of the other with respect to volume. But we're changing the fixed effects. Now the other thing we're changing too is the random effects. You'll notice that clearance follows a distribution A to 3, which is a separate variance and allows those individuals in this population to vary differently than those in this population. A to 4, and it allows different random effects between individuals than A to 2 for volume. So you can have different fixed effects and different random effects in the two subpopulations. Now, one thing that I've done here is I've set this up to allow for the different variability, but look in our omega block. What I've done is something that I would typically do to start, is to assume that they're the same. So A to 1, A to 2, that's our first block. And we're saying that that's the covariance between clearance and volume in mixture population 1. And A to 3, A to 4, that's the second block, the covariance between clearance and volume random effects in mixture population 2. I'm saying here that they're the same. Now that's not a requirement. That's just a first step. So we start maybe simpler here. If we want to add more flexibility and allow those to be different, then I'd remove same and specify a new set of initial estimates for A to 3 and A to 4, or for the variance of A to 3 and A to 4. Okay. I'll continue through the code and then I'll answer some questions. So the error block is the same as always. We have observed data y equals the prediction f times some exponentiated residual error. We have a mixture control record now, $mix. That's new. And there's one requirement for that. Well, there's two requirements actually. One is to define the number of subpopulations. So we're saying here we're going to propose a mixture with two subpopulations. N subpop equals 2. The probability of belonging to, or the proportion of patients belonging to population 1 and the proportion of patients belonging to population 2 are estimated. And of course, you only need to estimate one of those because the other one is the complement. It's 1 minus that proportion. So theta 5 here should be bounded at between 0 and 1, and you see here that it is. Okay, so P1 is the probability of, or I'm sorry, not the probability, but the proportion of individuals belonging to population 1, and P2 is a proportion belonging to population 2. If you looked at this from a population simulation point of view, it is the probability of belonging to one population or the other. Everything else is pretty straightforward, same old stuff. In the tables, we're including est here in the table so that we can capture the assignment to which population each individual belongs to. Okay, let me answer a couple of questions. Regarding covariates and mixture models. So the question is, if you explore all covariates before assessing the mixture model and then you do a mixture, would you have to redo the covariate analysis? No, and in fact, this I still like to fit this along with the pre-specified full model approach that I've advocated in the past. But you first do your covariate assessment without the mixture model, and then if there's remaining variability that you can't explain from anything that you've observed or from anything that you had pre-specified, then you would propose the mixture model. That mixture distribution is on top of the covariate effects and shouldn't impact the covariate effects. So you don't have to rerun any covariate analysis after that. You'd want to run the full model one more time to refine the estimates of the parameters. How many subpopulations can we try in NONMEM? Is there a limit? That's a good question. And I don't, off the top of my head, I don't have that answer. So I can dig that up and get back to you. But in reality here, we don't often deal with more than 2 or 3 subpopulations. Yeah, so next question, is there a reason for coding the clearance of population 2 proportional to that of clearance 1? Couldn't you just use a separate theta? Yes, of course, you could just use a separate theta. I think it's sometimes a little more interpretable if we're going to explain the results here by writing it in this fractional change manner, in that we can say, you know, that a given population has a clearance that is X percentage of some reference. That's sometimes useful. But you could do it either way. Is there a typo in the error model? Let's see. Y equals F times EXP to epsilon. I don't think so. This is a proportion. This is a, well, there's no typo here, but recall that because of the linear approximation that NONMEM is making, this actually collapses down to a proportional model. But no, that's a perfectly legitimate way to write the model. It just collapses down to proportional residual variability. So if theta 5 is 0.6, does that mean that 60% of patients belong to population 1 and 40% belong to population 2? Yes, that's the correct interpretation. What would the simulation code look like for a mixture model? Well, that's something that came up in the discussion board earlier today. And the way that I've done in the past is to specify a simulation of a categorical covariate. And if you recall back in the MI212 class, I showed you how to simulate a 2-category or a 3-category variable in NONMEM based on the uniform random number sampler. You would do it the same sort of way. You'd sample that uniform sampler, and then you'd say, we'd have our point estimate now of P1. Let's say it's 0.6, 60% of individuals. We compare that to our uniform random variable. If the uniform variable is greater than 0.6, excuse me, that individual will be assigned to population 2. If it's less than 0.6, they'd be assigned to population 1. So it's just like simulating a categorical covariate, except you use your cut point here based on the proportion estimated in dollar mix under P1. Okay. And I think that's it. No more questions at this point. Let's take a look at the NONMEM help again. And we'll go to examples. I'm just going to show you another one, mixture model. This is the phenobar population PK data set that's commonly used, but now viewing it as a mixture model. In fact, it's quite similar to what I just showed you. In fact, it's the same as what I just showed you. The only difference here, I didn't include the call flag here. The call flag just identifies how frequently the pred block is called with respect to the data records. You can look at dollar mix. There's some other options here. And this is that block where we specify the number of subpopulations. Maybe we can find if there's a limit here in NONMEM 7. NSPOP is an integer variable. The number of subpopulations must be given a value when I equals 1. So it has to be done on the initialization run. We don't know what the limit is from this help file. Let's see. For each of the populations, P1 is the model fraction, which we've already discussed. The sum of the P should equal 1. In principle, P1 can change from individual to individual. If for a given individual the second subpopulation doesn't apply, then set P2 equal to 0 for that individual. Mix P may be coded instead of P. They're synonymous. Okay. So the help is not too clear there on how many levels we can implement. I've never hit a limit, but I don't think I've ever done more than 4 or 5 subpopulations, and that was just as an illustration. I think most of the time we're going to deal with just a couple. Although recently we were dealing with an estimation problem for dextromethorphan pharmacokinetics, and dextromethorphan is a well-known CYP2D6 substrate where we could actually maybe identify poor metabolizers, ultra metabolizers, extensive metabolizers, and so on. And so that's one way you might try to approach that sort of a problem. Okay. Any more questions on mixture models? Well, our practice problem will be implemented on our lab session on Friday. And what we're going to do is look at a population PK model with some covariate effects. We're going to estimate inter-occasion variability in clearance over F, and then explore the possibility of a mixture distribution due to unknown covariates on top of that. And one of the things we're going to want to do is check assumptions, so we'll walk through that. I will post a data set and a model before our session on Friday. Now, because not everybody's up and running with SIMI here, I'm not going to ask you to do this hands-on by yourself. What I will do then is I'm going to teach you how to use SIMI, and we'll run through the problem together during the Friday lab, sort of an all-in-one session. And that will be, your introduction to the hands-on component. Those of you that took the 210 class last semester, you're going to be quite familiar with using SIMI and the MIfuns scripts. But those of you who have not will probably benefit from this. In the future, though, what we'll do is assign the homework problem for you to try independently. This week, you're off the hook. You can just listen in on Friday, and we'll show you how to do it. Okay. Any other news we need to review here? I think I've already told you about your assignment for this week. Sorry. So your assignment is to, well, number one, confirm that SIMI works, okay, and attend the lab session on Friday. That's critical that both of these are done this week, because if you don't get that far, we're going to have difficulties in the hands-on component throughout. In addition, I've also cited some literature references that could be useful for the next topic. So our next topic is going to be dealing with data below the quantification limit. And there are 3 papers here that are quite relevant. Try to at least read the first one. This is the most recent on likelihood-based approaches for handling data below the quantification limit using NONMEM 6. All of these methods are still relevant in NONMEM 7. This will be the topic for discussion next time. All right. I think that's all I had to cover for today. I'm going to just hold on a minute for additional questions. But you could use the extra time today to check your SIMI logins, get started on the readings, and of course, as always, post any questions that we didn't answer in class today to the discussion board, and I'll try to get through those before the next class. So I'll hopefully see you all online this Friday at 2 p.m. Eastern Time for the lab session. Thanks for your attention, and that wraps up today's topic.